Hello, everyone. It's my great honor to introduce our speaker for this lecture in climate data science. Tobias is a postdoctoral scientist who has studied meteorology and Earth system modeling in Hamburg. He works at the intersection of these fields with machine learning, with a special focus on generative models and data simulation. He explores how these methods work at an underlying level and how we can harness them to learn more about the physics of the Earth system. So with this, let's welcome Tobias.
Yeah, thank you for your nice introduction. I hope you can all hear me perfectly. Yeah, as I was introduced, I will speak today about generative modeling and specifically about generative flow modeling. And I will focus mainly on using these techniques for CS modeling. So CS is an important part in the Earth system. And I'm doing so because I'm part of a project which is funded by Schmidt Science. Um, and we have also partners in the US, partners in New Zealand, throughout Europe, and it is a pretty big project where we try to improve sea ice modeling. And today I have the pleasure to speak about how we can use generative modeling to improve our Earth system models. And I will also speak about in general two revolutions that happened or that happen right now in Earth system modeling. To directly jump into the first revolution, we have to make a small detour. We have to jump basically 6-7 years back. And this paper, Challenges and Design Choices for Global Weather and Climate Models based on Machine Learning, was one of the first papers that investigated how we can use neural networks, how we can use deep learning for numerical weather prediction. And back then, they showed figures like this. So here, this is the geopotential height in 500 hectopascal. And it is one of the most important variables for synoptic meteorology. And here we can see the red line is the neural network prediction, the error of the neural network prediction, and the purple line is the prediction of the state of the art numerical weather prediction model. And on the x-axis we see the lead time going forward. And so we can see after a lead time of 5 days, the neural network increases the error by 4.5 times. And even in 2021, Stefan Rasp et al. Concluded in a paper where they used neural networks for numerical weather prediction that it will be difficult for these models to compete with conventional physically driven weather forecasting. However, nowadays we have now neural network models, for example, the AIFS from the European Weather Forecasting Center, which actually outperforms geophysical models. So the AIFS outperforms the IFS, the geophysical model from the European Center. And this is what many call the data-driven revolution of numerical weather prediction. As I said in the beginning, I will mainly focus on sea ice modeling. And so a question is then for sure, can we also use deep learning to improve sea ice modeling? And the specific focus of this project where I'm part of, the so-called scale-aware sea ice project, is the so-called NextSim model. NextSim is a next generation sea ice model, which is developed around a new type of rheology, so a new type of parameterization of how the sea ice reacts on external forcings from the atmosphere and the ocean. And it is also built around fundamental processes in sea ice. So we know that sea ice is multifractal and anisotropic. So if we have a crack in in ice, this crack will propagate in a specific direction. So which means cracks act like linear kinematic features. So they are basically linear. And then sea ice is also very much characterized by rapid changes from open water to closely dense sea ice. So meaning within a few kilometers, we really have this transition from open water to dense sea ice. And so, which means sea ice is actually very, very difficult to model. And NextSim is I would say, a state-of-the-art sea ice model that tries to incorporate these processes completely for the mesoscale. Now, let's take this model and let's build a surrogate model. Let's build a neural network around this model to basically emulate this model. The general idea is we have our CS fields right now. So the CS thickness, the CS concentration, then the two velocity components of the CS, and then a specific variable, the so-called CS damage, which characterizes the subgrid scale fragmentation of the CS. And then we put these variables into our neural network, into a surrogate model, and predict what happens in 12 hours. So how do these 5 variables look like in 12 hours? As neural network here, we will use a unit with a vision transformer in the bottleneck, and we will simply minimize the mean squared error between our prediction and our target that we want to predict. For sure, CS is heavily driven by external forcings, and so we need external forcings. And here we will use as external forcings the 2 meter temperature, the 2 meter specific humidity, and the 10 meter wind speeds from RF5, so from the atmosphere. And we use these forcings for the initial conditions time, and then also for the time for that we want to predict. The data that we will use is data from this advanced CS model, and this advanced CS model has been coupled to the NUMO ocean model. And here I will use 20 years of data for training and 3 years for testing. In the beginning of this talk, I will just focus on a small region in the Arctic, as depicted here with this red rectangle. However, later in the talk, I will then transition towards Arctic-wide modeling. Now, let's dive directly into results. The results will look like this. So on the x-axis, we have the lead time in days. So we have trained our model for 12-hour lead time, and by autoregressively cycling this model, we can go forward in time, like in classical weather prediction. And then on the y-axis, I show the normalized root mean squared error, which is the root mean squared error that is averaged across all my testing data and across all 5 variables normalized by the climatology. And here, as truth, I will use the simulation from NextSim. For sure, we need baseline performances, and a very, very good baseline in CS modeling is the so-called persistence forecast, which is where we persistently predict the initial conditions. And so meaning it does not matter at which lead time we are, we just predict the initial conditions. And then this darker line here is a simple dynamical model, which takes also atmospheric forcings into account, and which, as we can see, which outperforms a persistence forecast. And then if we now look how our deterministic forecasting model works, then we can see that the deterministic forecasting model outperforms basically the dynamical model, and for sure it also outperforms the persistence forecast. And this is actually true for all times, for all of the 5 variables, which means that really that the deterministic model really improves how we can model the sea ice compared to a simple dynamical model and compared to our persistence forecast. This is the good side of the deterministic model. However, the deterministic model has also a bad side, and I will come to this. So here I show now a snapshot from a simulation from NextSim, and the snapshot is the CS thickness after 12 hours, after 7 days, and after 50 days. And here I show average energy spectrum in the CS thickness here in black next to them, so the geophysical model. And as we can see, after 7 days, the field looks very much the same as after 12 hours. However, after 50 days, we can clearly see that the situation has completely changed. If we now plot in how our deterministic forecast looks like, we can actually see two things. So first of all, if we look after 12 hours, the deterministic forecast looks not so bad at all. However, after 7 days, we can actually see that the deterministic forecast smooths the fields out. And we can actually also see this here in the energy spectrum. So in the energy spectrum, we can see that the deterministic forecast basically loses small scale information. So which then is basically the smoothing in spectral space. And then after 50 days, we can even see here artificial strains, which basically means that the deterministic forecast becomes unstable. And then if we further analyze how the fields look like after 50 days, so here once again we have in the first row what the original simulation from the geophysical model says. So we know from CS physics that if we have less sea ice, so this is the CS concentration. So if we have less sea ice, this also means that sea ice can be there more deformed. So we can clearly see here strong deformation where we have less sea ice. And also this is the change in the CS thickness within 12 hours. And we can actually identify features that are common. So for example, if we have a deformation, if we have a convergence, this means that CS can increase there because of so-called ridging. If we now look into what the deterministic model says, then the deterministic model clearly loses any physical consistency because as one can see here, these fields does not look at all like these fields in the top row. And actually the same was found for atmospheric forecasting. So there's a nice paper from Massimo Bonavita from the ECMWF, who looked into how well Pengu weather can model tropical cyclones and so on. And so this is the vertical velocity in 500 hectopascal. And this does not look at all like what we would expect from a tropical cyclone. So this means that also in atmospheric or in weather prediction, we have exactly the same problem. Also in weather prediction, our deterministic forecasting models lose any physical consistency. And this is actually caused by the optimization of the neural network, because the neural network is optimized to basically match the mean. It is optimized to by the mean squared error, and the mean squared error then induces a so-called double penalty effect. And this double penalty effect basically means that it is better for the mean squared error loss to smooth out features that cannot be predicted, rather than predicting just wrong features. And so we have to encourage somehow the model to make wrong predictions for the unpredictable scale. And we have to introduce some stochasticity into the problem. We have to make a stochastic prediction. And this brings us then to the second revolution, which took concurrently place, and this revolution is the revolution of computer vision. So in computer vision, we have now tools which can generate very realistic images. So actually, this paper here is a paper from Google Research from 2022, I think. So it is actually already 3 years old, and nowadays the generated images look much more realistic than this one, but this is kind of funny. And then now we have also models that can generate very realistic videos. So this video was generated by the latest video generation model from Google, which came out I think 3 weeks ago. And in this model, this model can not only produce realistic videos, but also produce realistic sounds together with the video. And nowadays we have tools to really to generate really realistic data. And for sure, the same tools can be also applied for numerical weather prediction. So we had, for example, once again, a paper from Google about GenCast, or a weather prediction model from Google, which is based on this technology. And then also NVIDIA has investigated this, and the latest paper is Climate in a Bottle, where they use this technology to basically generate new fields, to generate very realistic climate situations at very high resolution. And so, as we can see, this revolution of generative computer vision starts also now for web system. As I said, the nice thing about these tools is that they introduce stochasticity. And the general idea is to basically destroy information in the data. So remember, I've shown to you a power spectral density previously. And so let's focus a bit on this power spectral density. And let's focus a bit on what happens if so X is here our data, and what happens if we add noise at different steps. And if we add noise to it, then we can actually see that slowly the energy increases first in the small scales, and then until it basically overshadows all the information that is included in the data if we increase the noise. We can for sure also look into spatial maps. And here I will do a transformation. So in the first row, or here in the left figure, we have added noise, and here we basically replace information by noise. So which means that the process here represented in the first row is a so-called variance exploding process, whereas the process here in the bottom is at least a bit a variance preserving. It is a so-called sub-variance preserving process, because if we choose tau, for example, 0.5, the variance is smaller than in the original way. And so if we now go forward in space, then we can actually see that really in the beginning we basically overshadow, we basically destroy small scale information until we then destroy also large scale information. And the general idea of these models is then to inverse this process. So, which means if we now do it the other way around, then we can see that we first generate large scale information, and then in the end we generate small scale. And this means basically that we want to find a way of going from data to noise, or of going from noise to data. And if we want to characterize this a bit, then we can look at it like this: that we have here on the left our target data. This is the data we want then to generate later, and then we sample a random noise, and we have to connect these two somehow. And this connection basically defines the flow from going from data to noise, or the other way around. And for example, a possibility is to use a linear mixing between data and noise, which is possibly the easiest process of doing this. And actually, this process here defines an ordinary differential equation or a stochastic differential equation. It depends basically on the process we choose here. And the nice thing is that if we know the data, if we know the noise, we can simply go along this line here. So if we sample here a pseudo time step, either so this pseudo time step is between 0 and 1, and we can sample, for example, 0.5, then we would be here in the middle of this process, or 0.25, then we would be here, and so on and so on. So which means we can simply, if we know our data during training, so during training, we know our data, we want to learn to generate this data. And so we can simply draw a noise state in between. And the nice thing is then that during training, we basically know how to go from noise to data and to go from data to noise. And this is defined by the so-called by the velocity. So by the gradient of this flow with respect to the pseudo time. And this can be really seen a bit like the velocity that we have in the atmosphere that we see as wind. And so we can estimate this velocity during training perfectly. And the goal is then to use a neural network to basically approximate this velocity. And what we then can do is we can simply take the norm between our true velocity and our predicted velocity, and then train the neural network to take basically any noise, to take any pseudo time step, and so on and so on. So we train the neural network over a very, very, very long time. And then we have a neural network that basically approximates the velocity. And the neural network approximates this velocity without knowing what we want to predict, just by knowing what is the current state. The nice thing about this is that we can then use this neural network for prediction, actually. So if we want to generate new data with such a flow model, what we basically do is we sample an initial noise, which is truly random Gaussian noise, and which is actually stochastic. And then we apply our neural network to denoise a bit. And instead of denoising completely from the beginning to the end, we denoise in many, many small steps. And so until we end up with our clean generated data. And actually this defines us a dynamical system like we have in classical geophysical modeling, like we have in classical weather prediction. And actually this process is, as I said, a generative flow. However, there are many, many different points of view on this. So the let's say the flavor that is used most often are so-called diffusion models, which basically define instead of using an ordinary differential equation of defining the process, a diffusion model. It defines it as a stochastic differential equation. Then we have also score-based models. It can be also seen as hierarchical variation autoencoder, and then also quite recently developed as flow matching and as so-called stochastic interpolants, which basically map between two different distributions. And as I said, the nice thing is now that we can change here this initial sample to basically generate different samples here in the. But let's come back to surrogate modeling. Let's come back to emulators. So we want now to apply this process to generate new data, to generate basically prediction. And we can do so because instead of just taking any noise state into account, we can also train a neural network that is conditioned on initial conditions and external forces. And which means the neural network will no longer just decide on how to denoise basically, or how to go forward in pseudo time based on the noise state, but also on the initial conditions and so forth. And the nice thing about this is then once again we can change here the initial sample. In this way we can generate different ensemble members from the same initial conditions, from the same forcings, and then we can do with that ensemble statistics. So we can use an ensemble of predictions to create an ensemble mean. We can analyze the predicted uncertainty, and so on and so on. And if we do so, for the example that I showed earlier, so I've shown to you already this picture. Once again, on the x-axis we have the lead time, on the y-axis we have the weakness together. If we now plot in what here a diffusion model, what here a generative model says, then we can see that if we use a single ensemble member, the model is actually worse than the deterministic model. However, if we use the ensemble mean of 16 ensemble members for our prediction, then we can see that it basically outperforms the deterministic forecast. And this is kind of surprising because the deterministic forecast is really trained to minimize the mean square error, which is basically the metric that we use here to basically say how good our model is. Nonetheless, the diffusion model, which is trained with our proxy, outperforms this model. And we can also already see that if we would continue this line, we would expect that actually a diffusion model with a single ensemble member would outperform the deterministic forecast. And one can now ask, why is that so? The first thing is that, as I said, the deterministic model loses small scale information. However, if we plot now our generative model into this figure, we can see that so this is a single snapshot from a single ensemble member, and we can see that this single ensemble member keeps information at all scales. So we see that this also that the diffusion model basically keeps the information at all scales, can basically match the power spectral density of our true data, of our geophysical data. And we have also a pretty good match between our real data and what the generative model says, which is kind of surprising that we have even a pretty good match after 52 days. So if we now look once again after what happens after 50 days, then we can clearly see the diffusion model, the generative model, leads to really realistic settings. So meaning we can once again, as in our true geophysical simulation, we can track single features and match these features to changes in the CS thickness. So which basically suggests that the model has really learned some sort of equivalent of the physics. And if we look how the deformation is distributed, we can see that so here on the left, I show the shear deformation, a component of the deformation, and on the right the total deformation. This is in log space. So and the thing is that actually strong deformation values are the most important deformation values, and we can see that for strong values we basically more or less match what the geophysical model says. However, for small deformation values, we have less samples, and we can also see that this field seems to be still a bit more noisy than the original field. But nonetheless, as I said, the important part is the part here on the right side, and there the generative model is really good. And then the most interesting thing for me, at least, was that there is some sort of benchmark test case. So remember, the model is trained with more or less realistic settings. We have used the output of a real CS model driven by error 5 forcings. And here I'm now in a completely idealized setting. So here we have an atmospheric cyclone that will move from the lower left to the upper right of the domain. And then we will look here in the CS thickness, CS concentration, the speed of the sea ice, and then once again into the two components of the deformation and the total deformation. And if we let this run forward, we can clearly see how the cyclone moves even in the predicted sea ice fields from the lower left to the upper right. And if we look in how the deformation looks like after a few days, this looks very much like what we would expect from a real sea ice, from a geophysical sea ice. And then also what we can also see that at the end we see that the sea ice thickness is increased along the path of the cyclone, which is once again what we would expect from this ridging process of sea ice. So this means that this regional model really seemed to work for very idealized cases, and which basically suggests that this model generalizes well outside of what it has been trained in. Now comes the very big question: how to scale this model up? Because here I've deliberately chosen a model that just works on a 64 times 64 grid points. And so in diffusion models, in generative modeling, a problem is really how to scale these models. And an option that is very, very popular for image generation, for computer vision, are so-called latent diffusion models. In latent diffusion models, the general idea is that we pre-train an autoencoder that compresses our space. So, for example, going here from our 5 variables and 512 times 512 grid points to a latent space with 16 times 64 times 64 grid points, and then do this generative flow process, this diffusion process in latent space, and then use the pre-trained decoder to go back from the generated latent space into real data space. And the nice thing about this is that we can actually encode cryophysical knowledge into the process. So here we can train the autoencoder however we want, and so we can bake into the autoencoder, for example, that physical variables have a bound. For example, the CS thickness cannot be negative, and so we can bake this into our autoencoder, despite the fact that this generative flow process, that this diffusion process is heavily based on a continuous Gaussian assumption. And another nice thing is, because of this data compression, the whole generation process is 25 times faster. If we now look into what these models can do, so here I show now generated fields for the full Arctic. This is just a zoom into the central Arctic, and here we see in the first column the CS thickness, the CS concentration, then once again the speed and the deformation, and then we see in the first row our diffusion model in pixel space, and in the second row a latent diffusion. And if we look how the diffusion model in pixel space looks like, this looks very much the same as we would expect from realistic simulations. However, if we look into what the latent diffusion model does, we can actually see, especially here in the deformation, that the latent diffusion model seems to smooth out the fields once again. And indeed, this is what we see. So if we once again analyze the spectral density, then we can clearly see that the latent diffusion model loses once again small scale information, and this is actually not so good because in geophysical modeling we are really interested in the small scale information, and so we want to keep the small scale information in some sense. And this comes really through the variational autoencoder, through the compression technique. And so we basically reintroduce the problems with smoothing that we wanted to fight with our diffusion model, with our generative model. So we have to come up with another solution. And as a small reminder, I said to you that generative flows, diffusion models work like classical numerical models. Once again, we integrate here a predicted velocity in pseudo time. And so we basically really integrate a differential equation. And as you might know, in numerical modeling, we have basically solved this problem. In numerical modeling, we can really scale our models up to the kilometer scale. And this is because in numerical modeling, we have the trick of domain decomposition, and we can actually use exactly the same trick to scale up our diffusion model, to scale up our generative model. And actually, the same is very similarly used by NVIDIA, which they labeled as multi-diffusion. And the general idea is we have our full domain, and we split up our full domain into subdomains, and then we have overlaps between subdomains, and then each subdomain is processed independently, and we update always this core of a subdomain. So here indicated by this dashed line. And we can use exactly the same for surrogate. So based on this, I will now introduce the first efficient generative CS model that models how the CS develops in the mesoscale for the full Arctic. And the general idea is like introduced previously, we basically initially draw a noise and predict a residual. So how the CS develops within 12 hours, once again, based on given initial conditions and external forcings. And we initiate here a generative flow, which brings us then from the noise to the predicted residual. And then we can add this residual to our initial conditions to get our prediction for 12 hours. And then we can use these predictions once again as initial conditions to go forward to 24 hours and so on. As I said, we can use domain decomposition. So if we zoom into what happens in a single step, we have our Arctic-wide domain. What we then do is we basically take a subdomain. We split the full domain up into subdomains. We put this then into a vision transformer or a diffusion transformer, and the diffusion transformer then predicts the velocity, and this velocity is then used to update this cell or this subregion. And in the updating process, we basically neglect our overlapping regions, and we do this domain decomposition and then patching together process at each generative flow step, and this actually allows us to process the full field linearly in time, despite the fact that the transformer basically scales quadratically. And the nice thing is then we can train the neural network to do regional modeling, and we can train the neural network to do regional modeling for any sampled region. And this also facilitates training very much. And also this basically allows us to really localize the forecasting problem, because we know, for example, that the weather in New York is not so much influenced by the weather in Europe right now, and it won't be so much influenced, or the weather in 12 hours in New York will be still not so much influenced by Europe. And so we introduce basically a hard localization into our problem. And this allows us then, and the vision transformer then basically allows us to learn, on top of this, to learn a soft localization. And by using certain tricks, this model is then in the end independent of the chosen resolution. So it is trained across several resolutions. So it works between 10 kilometers and 100 kilometers. it is also independent from the used mesh. This is why I used here a vision transformer and not a unit or something like this, because in a convolutional neural network we always make a certain Cartesian assumption, and I wanted to avoid this assumption. And then also on top of this, this model respects physical bounds. So which means that in the prediction of this model, for example, the CS thickness can be never negative. It will be always bounded by 0, and there will be a lot of zeros, and yeah. So if we now look how this model works, then the first thing I show you here is once again the normalized root mean squared error. And here once again I show the persistence forecast, I show our deterministic forecast, and what the generative model says. The deterministic model is an Arctic-wide model, and we can actually see that if we compare this to the figure that we got for our regional setup, this is more or less the same figure. Once again, in the power spectral density, it is once again the same message. The generative model basically matches the power spectrum of Nexstim more or less perfectly, of our geophysical model almost perfectly, whereas the deterministic model loses information. And this is the power spectral density average across the full testing data set of 3 years and after 10 days. And then once again after 10 days, we can then also look into how well the CSH is predicted, because this is kind of important, for example, for shipping routes from Asia to North America, or from Asia to Europe, and so on. And so here we can see that the generative model even in this metric completely outperforms the deterministic. And then what we can then also do is we can look into our scorecard. So here I basically split the root mean squared error up into different variables. I split it up into different regions, numbered here from 1 to 11, and then in different seasons. So January, February, March, April, May, June, and so on. And I show here the root mean square error of the generative model compared to the root mean square error of the deterministic model. And blue means here the generative model is better, red means the deterministic model is better. And if we look into the scorecard, we can see that this scorecard is throughout all variables, throughout all regions, all seasons, almost always blue, which means almost always the ensemble mean of the generative model outperforms the deterministic model. It is, however, not the case for the first 12 hours, because as I said, the deterministic model is trained by a mean squared error, which is basically for the 12-hour lead time, the deterministic model behaves like a true ensemble mean, and so here in the generative model I use just 8 ensemble members, and so which means we have some noise on top of the let's say real ensemble mean. And so I would expect if we would increase the number of ensemble members here, I would expect that basically here in the beginning this becomes white, so that the ensemble mean behaves as the deterministic forecast for the 12-hour. And then a very nice thing is, as I said, this model is just trained for 12-hour forecast. However, nothing prevents us from using this model for very long-term simulation. So with this model, because a 12-hour forecast for the full Arctic takes around 1 second on a single GPU, which means that roughly we can have 100 simulated years per real-time day, and which means we can actually use this model to basically do our 24-year simulation. And here I show 3 different curves. So this is the CS volume independence of the year. And we have in red the generative model. In blue we have the true geophysical model, and in black a data assimilation product. And as we can see, the generative model is stable. It basically shows the seasonal cycle as we would expect it from observations and from the geophysical model, more or less. And it in general has similar features. However, we can also see that if we look into the results before 2007, we see that the geophysical model has a bias compared to the data assimilation product, and the generative model has an even bigger bias on top of this. And then afterwards it looks very, very good in some sense. And the reason of this is actually climate change, because sea ice is thinning because of climate change. So we have nowadays much more younger sea ice than here in the beginning. And so we have a so-called distribution shift, and it seems like the model is much better for thin sea ice than for thick sea ice. However, if we would analyze now the trend because of climate change, the generative model still sees a trend. However, this trend is not as big as for Nextstep or as for the data, which means the trend because of climate change is basically underestimated by the generative model. However, as I said, keep in mind this model is just trained for 12-hour forecast. It is not trained to give realistic forecasts after 24 years. Nonetheless, if we look into a field after more or less 24 years, we can still see the physical consistency. So we can still track single features in our fields. And for example, we have a huge crack here. We can also see this in the deformation as in the concentration, and we can see that the model predict that the sea ice thickness will decrease there. Or we can also track a feature here and so on. So meaning the model has really learned the physical relationship or the correlations between variables very well. Until now, I've spoken just about the Arctic. Another topic is for sure Antarctica, because in Antarctica we have also sea ice. However, we have less observations there. The processes are different there, and so we have for I think 2 or 3 months we have now simulations from this geophysical model. And if we look how the generative model performs in this completely different setting, this is actually a Cartesian grid. It is a completely different geometry than for the Arctic, and we can actually see that the generative model works pretty well for the deformation. So for the dynamics, how the sea ice deforms if we impose external wind forces. So we can for example really see we have a strong deformation here. We can track the same deformation in two different simulations with the generative model. Here we have a simulation at 25 kilometer, here a simulation at 12.5 kilometer, and we can clearly see that the simulation at 12.5 kilometer uses exactly the same model as for the 25 kilometers, and it seems like it is for sure it is at a higher resolution, but the learned features or the features are generally the same. However, if we look into the thermodynamics, this picture is not so nice at all, because here on the left we have once again what the geophysical model says, and we can see that the generative model says a completely different sea ice thickness field. And so there are actually two reasons why this is the case. So the first reason is that I just use atmospheric forcings, and in the ocean, in Antarctica, ocean forcings are very, very important, and so I neglected until now the ocean forcings. And then also I just trained the model for 12-hour lead time, and on 12 hours the CS is really dominated by the dynamics, and so which might indicate that it might be kind of difficult to learn the thermodynamics for shortly. And this brings me then slowly to the end of my presentation. So I've spoken about generative flow models for the Earth system, here specifically for sea ice. However, I would expect that these results hold also for other components of the Earth system. So for the atmosphere, we already see very similar things. And I would also expect that for the ocean, these results should more or less hold, and for the land as well. And I told you that generative flow models work more or less similarly like classical numerical models. And so we can use our tricks that we know from classical numerical modeling to scale these models up. Then I've shown to you that these models unlock an improved data-driven modeling, and that we get a physical consistent prediction, a physical consistent forecast. And I've shown you that despite the fact that this model was just trained for forecasting, we get stable and realistic long-term projections. And I've also shown to you promising results for extrapolation for really cases that are really, really out of distribution. These results were published already in 2 papers. So the regional setups are in this paper on the top. The latent diffusion model results are in the paper in the middle, and the results for GenSim will be available as preprints. And with that, I thank you for your attention. And do you have questions?
Okay, hello. Thank you so much for the talk. I had a question about how you structure your like vision transformer model.
Yeah.
So specifically you mentioned, sorry, it's a bit back.
Slide.
Yes, right there. So specifically, you mentioned that you choose not to use convolutions because of the Cartesian assumption,
Yeah.
but ultimately, like the 2D convolution tends to outperform the MLP just due to being able to like encode more spatial information. So did you find that if you did like some kind of Cartesian transformation on your input data and then used 2D convolutions that would lead to more like loss of information due to this Cartesian transformation as opposed to using the MLP in this case?
It is actually an interesting question. And I looked into this question already a few years ago. So actually, yes, I agree that basically using a Cartesian transformation, then extracting features in this Cartesian transformation, and then doing the final projection back into the original space can perform quite well. How the thing is, so I have what I've done. So the deterministic model is actually based on a unit together with a vision transformer in the bottlenecks, a so-called UVIT network, and I did a comparison test of just plainly using the UVIT for these subregions compared to this diffusion transformer, and I actually initially it performed better a bit, but it seemed like to actually smooth the features out more a bit. And yeah, and I mean, as we can, so it is an interesting question, but I would say that actually because the vision transformer performs already quite well, and actually spatial relationships are taken into account in the self-attention. So I use their rotary positional embedding rope to basically embed the spatial information, and this is this is basically how the vision transformer learned a soft localization. And with that, I really didn't see the need of any convolution whatsoever.
Oh, okay, yes, that makes sense. Thank you.
Nice talk, Tobias. Have you looked at something like a skill spread score to get a sense for how well the ensemble spread characterizes the errors in prediction?
So for the polar Arctic model, I haven't done it so much yet. I mean, but I have done it. I've done it for the regional model, and so actually there, the thing is that it seems like there for the tracer variables, the ensemble in the beginning was very good. However, it then, so the spread skill ratio, a spread skill ratio of 1 would mean a perfect spread compared to the root mean squared error, and we can see that the spread decreases with time. This might be because we have just a regional setup and so on. However, for the velocity, so for the dynamical variable of the system or variables of the system, we can actually see that the model is undiscursive. There might be many different reasons why this is the case, but I would actually my first look into the Arctic-wide results kind of looks similar in some sense. That the model tends to be undiscursive, but in general, I mean, if we looked at so I showed here just a snapshot of a prediction. So we have here the true field, what is predicted by next sim. Then we have the ensemble mean. This is the error between these two fields, so mean minus next sim, and then we have here two ensemble members. And if we look how the ensemble spread with 8 ensemble members look like, then we can actually see that the features are very much the same as for the prediction error. However, as I said, the spread tends to be a bit too small, despite the fact that we have very similar.
Hi. Yeah, thank you for your talk. I just want to make sure it's clear because we have a lot of young people in the room. What you're doing is not using data to train your model. You're using a different model, a physical model, based on physical principles.